The typing rule for let expression is more complicated. Let's consider a naive implementation of the let rule. For example, we want to type check the let expression, say let x equals to e1 in e2 have type t2. The trivial way is that we just need to make sure that e1 has a type t1, and then under the extended type environment with x bind to t1, because now x is actually equal to e1, and we want to type check e2 as a type t2. This looks very intuitive and simple, but it does not accept the following program. So in this program, we have a function f that is an identity function that takes an x, return x, and we have a function g which take in two arguments x and y and return the first argument. So, and if we have g apply to f apply to 1 and f apply to true, we get into trouble because none of the let rule premises allows us to promote the f to have a polymorphic type, because once we have 1 applied to f, we were expecting f is from type int to int, and that information is captured in the environment and propagated to the other side. And when we try to type check the f applied to true, and this would raise a type mismatch because now f has already had type int to int, but the incoming arguments of type bool, and we have a type failure. I will run an example in this written derivations. So we would like to prove that this expression have type integers. By looking at the shape of it, we have a let expression. So naturally we apply the let rule. And to do that, we first need to prove that this expression will have some type from int to int. Since this is a logical proof system, we can actually try to test by assigning some type. So in this case, we try to prove this to have type from int to int, and then we can apply the abs rule since this is a lambda abstraction, and then we need to prove this. For simplicity, we omitted the one extra step which applied the var rule because it's a variable, but it's obvious enough that we can prove that the x have type int. Then we look at the second part of the proof, where we need to prove the expression in the int part would have the types int under the new environment, where we extend the empty type environment gamma init with the f binding. And for now, let's call this is gamma 1. And we would like to prove that this expression, let g equals to this lambda in g applied to f1 and then applied to f true to have type int. So to do that, again, this is a let rule to be applied. We look at the first part. We need to prove that this sub-expression will have some type that from int to bool to int. Okay, and we follow these derivations. We can prove then again by the abs rule, say that the body has type from bool to int, assuming that x has a type int. And then furthermore, we can apply the abs rule again, and to prove that under the new environment extended with y of type bool, and prove that the body of the lambda abstraction has type int. So this is trivial. Then we move on to this part. For now, let's extend the gamma 1 with a new type binding about g, has type int to bool to int. Let's call this as gamma 2, and under which we want to prove that the expressions in the int part, okay, g applied to f1 and applied to f true will have type int. So due to some space constraint, I have to write the two subderivation on the in the space above. So obviously this is an abs rule. So there are two parts of the subproof. First, we like to prove the function expression part will have type from bool to int. Again, we are just guessing that this is a bool, and we can prove it because this is an abs rule. We can prove that first the g, which is a function expression, will have type from int to bool to int. Okay, this is a trivial proof by the var rule because g already exists in our extended type environment gamma 2. Next, we would like to prove that f applied to 1 will have type int. So this can be done easily by the abs rule because this is a function application, and we can look up from the environment find that f actually has type from int to int, and the constant one has type integer. So this is all okay. So let's consider the second subproof from this derivation, and you would like to prove that the f applied to g has type bool. Okay, since this is an app rule, we would like to first check that the function has type from bool to bool, but then because in gamma 2 we can only find that f has a type int to int, so we get back int to int, but the actual argument true itself is of type bool, and while the const true, and we have a clash of type here because the actual argument type, which is bool, does not match with the formal argument type, which is int. Therefore, there's a type error here.